All right, we are good to go and live, everyone.
Just go ahead and give it 1 minute till 10 o'clock and then we'll get started.
Do you just want me to start exactly at 10 then?
I'll go ahead and just mention the Mentimeter site, and then I'll go ahead and stop sharing so that everybody can see.
Okay.
All right, it's 10 o'clock, so we can go ahead and get started. Thank you all for joining us today. Just a quick note here, as you're watching the presentation, if you go to www.menti.com, and it will ask you for that code right there, 7655149. And when you go there, you can ask any questions for our speakers, and I'll make sure that at the end of the presentation, the speakers will have a chance to answer any questions you have. And now we're going to go ahead and send it over to Caden, and he's going to introduce our speakers.
Yeah, so we will be demonstrating the general principles of electrical arcing. This occurs when the potential difference between two surfaces is enough to cause a traditionally non-conductive medium such as air to break down and turn into a plasma, allowing the electricity to flow through and often emit light. We will be demonstrating this with either a Jacob's ladder or a Van de Graaff generator. A Jacob's ladder is two vertical metal rods for which an arc is started at the bottom. Since the air is being ionized and heated up, it will rise and subsequently so the arc, causing a cool visual effect of an arc climbing a ladder. The Van de Graaff generator is a large metal sphere which uses an internal belt to create a potential difference between the large sphere and a wand with a smaller sphere. This one is fun because we can either use the wand or you can use your hand or any part of your body as the ground as well. Don't worry though, the current is too low to harm anyone, but it's still a little shocking to the touch, pun intended. The concept of arcing is the main driving force, quite literally, in our arc jet thruster on campus.
All right, thank you for that great introduction. So I'm going to go ahead and share our screen. We have a small PowerPoint to get through, and we're going to start talking about kind of our research here on campus. So I'll share this. All right. All right, so I'm Austin Luttrell. I'm a senior here studying space physics at Embry-Riddle. I'm on this research project, which is our electric propulsion undergraduate research project, as well as an optical research project here on campus. I'm also a cross-country runner here at Embry-Riddle, and so I do that on my free time.
Right. I'm Ryder Moreno. I'm also a space physics major, a senior as well. In addition to being the co-team lead with Austin on this project, I've done research over at Los Alamos National Lab through the school, working with particle physics. In my free time, you can find me riding my bike around town or watching birds. I love birds.
All right, so we're going to go ahead and get started. So like Caden mentioned, the whole presentation will be centered around electric propulsion and the concepts involved with that, specifically electrical arcing. So a brief table of contents just to go over kind of what we'll be explaining today. So we're going to explain what our research is, what we do. Then Ryder will go into some definitions surrounding propulsion and thrust to give you some background as we kind of explain these systems a little bit more. We'll kind of go into the different types of propulsion, classical and otherwise. And then we'll kind of dive more into the real heart of the presentation, which is electrical arcing and how that plays into our actual electric propulsion system. After that, we'll kind of go through a little bit of history regarding this concept, how far it dates back and things like that to give some context. And then we'll actually show you guys a really cool demo. We have the Jacob's ladder today. We weren't able to get the Van de Graaff, but Jacob's ladder is really cool. And then we'll also get to show you guys our actual arc jet thruster that we've built here on campus. And then we'll finish it off with some questions. So Yeah, so to start, we'll just kind of quickly explain what we do, what the goal of our research project is. And I just realized that this is probably showing. Move that up here. So what we do, the goal and focus of our research project here is to explore exotic concepts in electric propulsion. So that's really involving with different types of thrusters, the kind of thrust outputs you get from that. And we'll explain all these kind of larger words that we're throwing out here in a little bit. We've currently built 2 ArcJet thrusters here on campus, the most recent one just being done this January. And so we're planning on doing a lot of testing with that this semester, as well as designing and building a highly sensitive thrust stand that actually allows us to measure these super low power thrust outputs from these systems. I just throw out a bunch of big words. Don't worry, we'll get to all that in just a little bit. Sorry.
All right, so to get on to some definitions to start with, I promise I'll try to make it not as boring as possible. First, I want you to just look at this, we'll call this a propulsion system in front of you, which is the example of a cannon launching a cannonball. So some main definitions in the things we'll be talking about are propellant and thrust. And a propellant is really anything that you're throwing out of a system in order to get a reaction out of it. You know, Newton's third law, every action has an equal and opposite reaction. So by this cannon launching the cannonball out, you can see in this GIF, it's being thrusted backwards, we would call that if we're talking about a propulsion system. And so in this case, the cannonball is the propellant, that's what's being thrown out. And then the cannon is being thrusted upon, that's the work being done to push it back. And then another small definition, which we won't go as deep into, is the accelerant in this propellant system. In this propulsion system, the accelerant would be the black powder. That's what's accelerating the cannonball to cause it to be launched out. And then now I'll go ahead and explain some actual rocket systems which you may be more familiar with. So when we're talking about actual propulsion systems, we like to break it down into 2 systems. There's classical systems and then exotic systems. In your classical systems, the propellant and the accelerant, which I was just talking about, the cannonball and the black powder, are actually the same thing. So that's where you have your chemical reaction rockets, which is what most of you are familiar with when you think of a rocket. It's a big explosion that launches a bunch of smoke and other particles out. And because both the chemical is the explosion that's happening and it's what's being thrown out of the rocket, we would consider this a classical system of propulsion. Now, the other system that we have is exotic systems. And this definition is pretty easy. It's basically anything that's not a classical system. And by that definition, we have the accelerant and the propellant are different. And so the electric propulsion that we're doing on campus is a type of exotic system. And I'll let Austin talk about that electric propulsion.
Yeah, so you've heard us throw the word out several times already. But so what is exotic or electric propulsion exactly? So like Ryder was talking about, all the different types of propellant and accelerants. So in electric propulsion, and I'll just kind of read through this definition so you don't have to read it yourself. So a type of propulsion system that uses electrical power to heat up and expel a propellant at high velocities in order to produce thrust. So like Ryder threw out a couple times, so we have the accelerant and propellant in a system, right? So in these electric propulsion systems, the accelerant in our case is going to actually be the electrical arc that we'll explain in a little bit. So that's when you actually have this electricity arcing through between 2 surfaces, and it's heating up the propellant, which in this case is a form of gas. And so this electrical arc is heating it up to crazy high temperatures, creating a plasma and sending it out the back. And so when you think about classical systems, you're getting actual like kind of mass that you can really wrap your head around, like, okay, you're burning all this stuff and it's being all thrown out. But when you think about these electric propulsion systems, you're talking about these masses that are just ions and particles, these tiny little things being shot out the back. And so the actual thrust outputs of these systems is super low, because when you think about like the mass of a particle, it is, I mean, it's too small to really even comprehend without having a deep understanding of the physics behind all of that stuff. And so you can kind of see in this picture on the PowerPoint here, this blue glow. So that's actually just all the particles in this gas getting ionized and shot out the back of this system. And so these super low thrust outputs, you might be thinking like, what's the point? Like, why would you even care about making these systems if you can barely even go anywhere with it? Well, it all comes back to this other concept, and it's called ISP. So ISP is like the fancy rocket way of saying gas mileage when you think about it in terms of like a car. So it's how much fuel you need to go kind of a certain amount of distance. So the main reason that you want an electric propulsion system is because it has great ISP, like significantly better than any classical system out there. So when you have like these satellite systems that are going to be orbiting the Earth for 5-10 years, and you want it to be up there without you having to worry about, okay, how often do we have to go up there and refuel this thing? How often do we have to bring it back down to Earth and service it? That kind of stuff. Having a really great ISP means you don't have to. It means like you send it up with an initial amount of mass and fuel, and it'll just stay up there for 5 years because the ISP is that good. So it's like having the difference between this giant truck that, sure, it's great for going off-roading, but when you're going on a big road trip, do you really want a big truck with terrible gas mileage, or do you want like a Prius with fantastic gas mileage, right? So when you think about it in terms of that, it has a lot of benefits. It's just not perfect for every sort of mission. So that's why it's primarily used in satellite systems or things that you already have up in space, but not really for getting to space. So now I'll hand it off to Ryder, and he's going to explain, like Caden mentioned at the beginning, what actual electrical arcs are and how it kind of ties into our whole system.
Yeah, thank you, Austin. So electrical arcs, I'm sure many of you, if not all of you, have seen electrical arcs in real life. The best example I can give of that would be lightning, like you see on the screen right now. But the analogy I like to use is the river analogy, where if you think of a river and where it flows, the river will always pick the path of least resistance. The rivers are always going to flow downhill. They're going to flow towards the softer soil, towards the less compact soil, etc. And electricity behaves in a rather similar way, where if you have electricity flowing through a wire and you have a great enough potential difference between that wire and another one, and even if you just place the wires close enough, the electricity will actually go through the air. It'll actually ionize the air and cause it to be able to carry the electricity, the electrical current, and it'll go across the air. And that's what you see when you see lightning. It's lightning coming from the clouds down to the ground. You have your high positive potential in the clouds and your very low negative potential in the ground. And that causes these electrical arcs that are massive and may have thousands of volts in them. But in our system, we have something similar where we're doing something very similar, but we're actually just pushing our gas through it to ionize it and give it more velocity, greater energies, so that it will give us a higher thrust output. And right now we actually have a demo for you guys. I'm going to go turn off the lights because it's a little hard to see.
So I'll stop sharing,
Yeah.
and so we'll just kind of show you guys with our video. So hopefully you guys can start to see this all right.
And so you can see at the bottom, you can see a tiny little arc. And this is our Jacob's ladder demonstration. So it's two long metal rods in parallel, and there's a very small gap at the bottom, and a very large electrical potential is put across these wires. And so at the bottom, a tiny arc forms. And then because the arc is hot and causes the gas around it to become hotter and ionized, and also because of the fact that hot air rises, as I'm sure a lot of you know, the arc actually travels upwards and then it goes towards the top of this ladder that we have. So We'll let this run a couple more times. This is basically exactly what's happening inside of our thruster when we're ionizing gas and causing it to move faster.
Okay. All right, so I'll go back to sharing my screen so we can get back to the, all right. All right, so now that you guys have actually seen these electrical arcs and you kind of have a better understanding of how our systems actually work, we'll kind of explain the brief history regarding this whole concept. So here EP stands for electric propulsion. So if any of you are really interested in rockets, rocket systems, I'm sure you probably have heard the name Goddard. So he is kind of considered the grandfather of all rocketry. NASA has a whole center named after him. He has revolutionized the whole rocket industry. And so he is actually the one that first came up with the general concept of these electric propulsion systems. And it dates all the way back to 1906, which is pretty insane to think about. Because when you think about, the first time that we set foot on the moon, right? That was in the 60s, right? And so when you think 60 years prior to that, we already had the concepts for these systems that would be used in high-tech satellites today in the modern age. Like, that's pretty wild to think about. And so, of course, they didn't quite have the technology back then in 1906 to actually implement any of these. And so it wasn't really until about 1948, right after World War II, that they actually started to do some testing with these systems. And so they didn't have the same kind of access to these renewable energy sources like solar panels or anything like that. And so they actually had these really big, heavy batteries that they had to use. And it was super inefficient, and it just wasn't really viable at that point. And so once we started to actually go deeper into the space race, and we started to put people on the moon, we started sending up way more satellites, it became way more viable, and the technology of the day was at a standard to where we could actually implement a lot of these systems in ways that actually mattered. And so it wasn't until the late 60s, really 70s and on, that we actually started building these systems. And so now in the modern day, pretty much every single satellite that you see up there is going to have some form of electric propulsion system on there, because their service lives are so long, like I mentioned prior, that you really want these like high ISP systems so that you don't have to come down and replace these satellites year after year after year. You can keep them up for a long time. And so we really do have the technology, and we can really thank all of that way back to Goddard for having the concepts for these systems and for them to be so fleshed out now. And there's still so much research to be done on how we can make these systems greater so that we can go into really deep space travel, because that's where this is really all hopefully leading one day, is that we can implement these systems on deep spacecraft that will allow us to get from here to Mars in less than a year or 3 years, however long it takes, but that you don't need crazy amounts of fuel for these chemical systems to get you there in a reasonable amount of time. So now that we've kind of explained the history of it, what we're doing, the concepts regarding everything, we'll tie this all back into what exactly we have done, what we're building, what we're doing, everything like that. So I'll explain what the arc jet thruster is that we have built, and then I'll let Ryder explain afterwards what the thrust stand is and why we need it, what's the point, right? So an arc jet thruster is a type of electric propulsion system that uses electrical arcs to ionize and expel propellant out the back to create thrust. So I'm sure that sounds exactly like the definition of everything else, but there are several different types of systems like Hall effect thrusters, magnetoplasma dynamic thrusters, that kind of stuff that I highly encourage you all to look up after this, but it's not quite in the scope of the time we have today. So in our specific system, we use nitrogen gas as a propellant. And so if you can see in this little diagram that we have at the bottom in the PowerPoint, you've got this long system. So you've got this tungsten cathode, and you have what in the top right, you can see this kind of nozzle cathode, or nozzle anode, sorry. So it's the potential difference between these anode and cathode, which are just kind of physicsy words, that actually creates this electrical arc like Ryder was describing earlier. And so we are using tungsten as our rod, and we're using brass to have this inner casing or outer casing around it. And so you can also see in kind of these dashed lines surrounding this tungsten cathode here, that's an insulator. So the point of an insulator in this system is to make sure that you don't get unwanted arcing. So as you saw in the demo, you have these two long rods, and you can see the arc travels up them, right? But we don't really want this arc to travel along the whole system that we have, because then you get the gas getting ionized way early in the system, and it builds up pressure in places that you don't want. And then it just kind of wastes a lot of the propellant that you really kind of need in these systems, right? So in our system, we've actually used boron nitride as an insulator that actually just surrounds the tungsten cathode so that it doesn't arc with the surrounding brass until a very specific point. So you can see on the right where the tungsten cathode comes down to a point inside this little kind of tunnel here. So that's where you want the most arcing potential, because as it arcs across that tiny little surface, all of the flow of the propellant gas flows through that tiny tunnel. And so you maximize how much of that gas that you're actually heating up and ionizing and accelerating out the back. And so as the tunnel expands out here, that's where the nozzle is, and that's where actually all the thrust is going to be produced and shot out the back. And so in this case, this thruster would be sending it to the left, the thrust would be coming out the right. And so, yeah. And so I will stop sharing my screen once again, just so I can kind of make sure I'm seeing everything correctly. And I'll kind of show you guys the components that we have in the thruster that we've actually built. So we unfortunately forgot to grab the actual tungsten cathode, but just for reference, it's just a long, thin rod. So this is our boron nitride insulator. So you can see it kind of comes down, converges to a point. So it's slightly different than the diagram that you guys saw earlier. There's a little tiny hole out here. You can kind of see all the way through the back. And so that slides right into this big, heavy brass nozzle. And so this thing is really hefty. And so you see this hole up front, that is where this slides in, just like this. And then you have this nozzle exit here. So if you can imagine, the rod is going to be coming in right there. It'll be sitting right at the tip of this where the hole is. And then this lines up to another hole in this big brass piece that comes out to this exit. So as the gas flows through that tiny spot, gets heated up, accelerated, and expands out here, that actually maximizes how much thrust you can get out the back. Mm-hmm. And then, so we also have this front piece. And so this is what actually holds in the boron nitride and the rod. And so this actually just screws on to the top there. You can see kind of all the screws. I'm trying to hold it together for you guys. And then you can also see this big tube. And so this is actually where the propellant is going to be flowing in to this little section here. We'll have this mounted. The rod will be coming in through here. And so you actually have the propellant come in, flow through the system here, and it's all encased in this. We're hoping to get arcing right in there in the hole and then shoot out the back. Mm-hmm. So hopefully you guys can kind of visualize what this system is. This is just one of the two arc jet thrusters that we have actually built so far. That's the older one. We have the newer one in this lab right now. So we just grabbed one. They look very similar to the naked eye. So we didn't think it was super important to show you guys both. I'm going to share the PowerPoints again, and then I'll let Ryder kind of take it away and explain the thrust stand that we have built and kind of the reasoning behind that.
Yeah, so there's two main considerations to think about when you're talking about the arc jet and when you want to measure the thrust output of the jet, because it's very important to know how much thrust you're actually producing. I mean, we know it's going to be very small, but if you want to get put onto a rocket or some sort of system later on, a satellite perhaps, whoever you're making this for has to know how much thrust you're producing. So it's very important to be able to measure our motor here. And the main two considerations you have to take into account are that the thrust output is so small, so your instrument must be sensitive enough to measure those tiny differences, and also the operating conditions of the thruster, and that would be space. And in space, there's no air, it's a vacuum. So on campus, we actually have a vacuum chamber that we use to put our thrust stand in and our thruster, and then suck all the air out, put it down to vacuum, and then we can test it with a nitrogen inlet and stuff like that. So our thrust stand was designed with those two conditions in mind. So our thrust stand uses all components that are just as well to be used in a vacuum as they are on Earth. So we have these very special flexural pivots, they're called, that allow us to know the exact torsion rate and spring rate, and kind of that allows us to determine the thrust output simply by measuring the displacement of this thrust stand. So this thrust stand was designed by us on campus, and it's been being built on campus. It's currently being built right now in the machine shop. So we're waiting for that to be completed. And then once that's done, we can hopefully measure the thrust output of our old thruster as well as our new thruster, and compare the differences between them and see what sort of parameters we changed and how that affects the thrust output and the general running parameters of the system. So now that we've kind of talked about the history and what we're doing in our project, we kind of just want to tie this all together with some general examples, both in real life and in science fiction that you've probably seen, to help you realize how electric propulsion affects your life today. And the main thing that electric propulsion thrusters are used for are satellites. Like Austin's been saying, you don't want to have a satellite that you have to refuel every 5 or 10 years. And electric propulsion systems are great for that. Their ISP is super high. Their lifespan is amazing. You can go by with just a couple kilograms of some propellants, like some nitrogen, like we're using, or xenon or krypton. And they're really great for that. And because when you're maneuvering a satellite, once it's already in space, you really don't need much thrust output. There's no air in space to cause drag. The gravitational forces are much less difficult to overcome. So you can really do your orbit transfers and those sorts of maneuvers, your rotations, position to be able to communicate with. These are all really great uses for electric propulsion systems. And if we're going to the science fiction sector with a little more advanced propulsion systems, one of my favorites series and movies and universes is Star Wars. And I hope you guys love Star Wars as much as I do. And one of my favorite ships from Star Wars is the TIE Fighter. And if you're a big Star Wars buff like I am, you would know that TIE stands for Twin Ion Engine. So then you have the Twin Ion Engine fighter. And so that's basically two very large, obviously the thrusters in Star Wars output a lot more thrust than what we're talking about. But I really love those fighters with their 2 ion engines. You can see the blue coming out the back. I'll let Austin talk about his example.
Yeah, so down in the bottom right, I don't know, you guys are young and Ryder and I are old now, but another really great universe that everyone knows about in science fiction is Star Trek, right? So down in the bottom right-hand corner, you can see the USS Enterprise. And so kind of the telltale sign of a lot of electric propulsion systems, specifically ion thrusters and Hall effect thrusters and that kind of stuff, is that characteristic blue glow. And so down in the bottom right-hand corner, you can definitely see that very blue glow off the engines of the USS Enterprise. And it's super cool to see. I know one of the rocket systems in The Martian, which is also a really great book and movie, uses electric propulsion systems. And really all across science fiction, you can see them in little places that you may not have before. So I hope as you go forward, kind of looking at all that fun stuff in your TV shows and movies, that you'll start to notice those kinds of things because we told you about it. So I hope this was really helpful. I hope you guys get excited about this kind of stuff. And so that kind of does it for our presentation on our research. And now we're going to open it up to questions for y'all. So I'll stop sharing my screen and let you guys kind of ask some questions.
There is just a slight lag time for the live version, so I just want to give it a few minutes for people to go ahead and ask any questions that they have.
Yeah.
Awesome. Sounds good.
While we're waiting on that, what got you interested in this field of study?
So for me, and I'll go first because it ties a lot into him, is that Ryder is actually the one that got me interested in it. I initially went into space physics just because I like space and I thought it was cool. And then about sophomore year, Ryder mentioned that he was doing a propulsion minor. And I pretty much just thought, oh, that sounds cool. And so I took a class or two with him and I found I really had a good passion for it. And then I started to get involved in this electric propulsion research, and it's just really cool and interesting stuff to be a part of. And it's such a big field right now that it's hard not to get excited when you see, like landing a Mars rover just last week. So I think that's pretty awesome.
Mm-hmm. Yeah. So when I actually didn't find out about Embry-Riddle until December of my senior year in high school, when I was taking an astrophysics class, and a recruiter from Embry-Riddle came to my class and they were talking about the space physics major program. And they were describing how one of the 3 areas of concentration that they have is exotic propulsion. And that just, those 2 buzzwords got me going right there. I was like, exotic propulsion, like, what does that even mean? I had only heard about chemical rockets and liquids and solids and those sorts of things. So it was really interesting to see this new, well, I say new to me, but it's been around since, like we've been saying, the last 100 years, this new field of, we've been getting to Mars with rovers, we've been getting to the moon, how can we do that more efficiently? And once I came on campus, I met Dr. Smith, who's a great mentor. I love him. He's one of my favorite professors. And I asked him, I was like, hey, is there any research I could get involved with? And he was like, yeah, we have this electric propulsion team where John Norton, the previous team lead, was working on it. And we all got together and kind of butted heads, but we all worked together and we've been loving the things we do. And I love trying to just research new potential ways to do things that we've been doing in the past and learning from our experiences. It's great.
Yeah, so I see that there's a question in the chat. So the question is, how did you create the pieces you showed? How long did it take? So the ArcJet that we showed was actually built prior to either of us being on the project. But we can kind of explain how we went about creating our ArcJet thruster. Very similar design. There were a couple of key components that we changed, but same materials and everything. So we started with just kind of getting a design concept. We pulled a lot of pieces from the old ArcJet project that they were going through, but also a lot of other research sources online. I mean, there's a bunch of research into it right now. So we got kind of the base design for it on paper. Then I taught myself CATIA actually, and then I mean, it's all basic geometry, so it wasn't that hard. And so we modeled these systems in CATIA, which is like a 3D modeling program. And then we created drawings out of that. And then we sent it into the machine shop here on campus. So Ryder and I, neither of us are actually machine shop certified. So we didn't machine any of the parts ourselves. We just gave all the dimensioning, the concept and everything to the machinists here on campus, and then they built it. So as long as it took, that's kind of a hard question because we submitted the design right before winter break, and then they didn't get to it until after break. So I would say probably in total it took them about 3 weeks. And that was like not working super hard on it because they have a lot of other projects too. So it was about 3 weeks for the machining part, and then it was about a semester's worth of design input as we worked to just some very small parts that would affect the efficiency a lot. And then another question for me.
Yeah.
So how do you manage cross country with the academic demands of your major? So the best advice for that is just time management. We have morning practices. So I run at 6 o'clock every day with the team. And then I have classes pretty much all day, usually from about 9 a.m. to 3 p.m. So it is very taxing. You're busy a lot. There's not a lot of time for outside stuff to do, but I love it. Collegiate running is a blast. You get to see some really awesome people, and our team is really good, if I can just boast on our behalf. We are NAI, so we're not NCAA, so we don't stack up against like big schools like NAU or anything, but we did get 4th at nationals for NAIA, which is very impressive. It's about D2 level for NCAA when you think about it that way. And yeah, so it's hard. You do have to manage your time really well, get ahead in classes. You can't procrastinate really at all, or else it just stacks up and becomes impossible. So it took me about a year to figure that out. And then the past 3 years were all right.
Thank you so much. I think that is all the questions we have at the moment. Really appreciate you guys sharing all that amazing information with all of us, the students especially, and hopefully setting their path to, if anyone's interested in that, to follow in your path. And it's great information, and we really appreciate you being part of STEMCon.
Yeah, of course. Thank you for having us. We really had a good time doing this presentation.
Yeah,
So.
thank you.
All right, see ya, everybody.
Bye-bye.